Welcome to Center of Math's Unusual Properties in Math. Today we're going to give two examples, one of a convergent sequence that has a divergent rearrangement, and also of a sequence with a function with a divergent integral and a convergent sum. So the alternating sum, the sum for n equals 1 to infinity of minus 1 to the n plus 1 over n, the signs are alternating. This term goes to 0 as n goes to infinity. And so this, in fact, is a convergent sum. And this relates to absolute convergence, because if we take the absolute value of each term, this becomes a harmonic series, which is not convergent. So this is not absolutely convergent, but if we don't take the absolute value, it is convergent. So this is convergent, but also we can rearrange it so it, in fact, diverges. And to do that, note the minuses and the pluses of both divergent sequences. So if we just took minus 1/2, minus 1/4, etc., that's minus 1/2 times the harmonic series, which is divergent. 1, 1/3, 1/5, same thing. It looks like the harmonic series, so it diverges. And so to rearrange this such that it diverges, we can do it as we can take 1, then do minus 1/2, then do plus 1/3, plus 1/5, etc., until we get just above 2, and then do minus 1/4. And then we keep adding terms until we get just above 3, then subtract the next negative term, then continue on this way. And so in this way, we'll use all of our terms, but the series will not converge to anything. It will diverge. And in fact, since this is does not converge, is not absolutely convergent, we can really rearrange this to get any number on the real line. So an example of a function that's positive and continuous with a divergent integral and convergent sum, and it's defined for on 1 and x greater than 1, x greater than or equal to 1. So we'll say gn functions, we're start with some function g of x, so we say g of n equals 0, n greater than 1, and n an integer. And then on the closed intervals, n minus 1 over n, comma n, and n, comma n plus 1 over n, we're going to say n equals 1 at the non-integral endpoint, so n minus 1 over n and n plus 1 over n. And between them, it's going to be a straight line. So we'll say g of n is linear between the two endpoints. And then everywhere else where we haven't defined it, we'll say g of n equals 1. So g of n is going to look something like, at all the integral endpoints, is going to be 0. At the integral endpoints, it's going to be 0. Between the points, we're going to have some linear section going up. So for 2 minus 1/2 and 2 plus 1/2 are both going to be 1, and between those two sections, it's going to be linear. And then once we reach an endpoint, it's going to just be 1 for some time, and then it's going to go back down to the next point, and etc. And note these closed intervals, as n gets very large, their length is 2 over n, so it becomes smaller and smaller. And so this is going to look more and more like kind of like teeth. And so define f of x equals g of x plus 1 over x squared. So this is a continuous and positive function. The integral from 1 to infinity of f of x is infinity. The sum from n equals 1 to infinity of f of x is the sum of 1 over n squared, which is a convergent sequence. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. If you like this video, please check out the other unusual properties in math videos in our playlist. Thank you.